Nuclear energy. The first commercial nuclear power plant came online in 1954 and marked the beginning of the so-called atomic age. Nuclear power has been and continues to be a highly controversial form of power generation. As of 2014, more than 100 serious nuclear accidents have occurred. Still, the International Energy Agency recently reported in 2020 that worldwide output for nuclear power plants is the equivalent of 517.8 million tons of oil equivalent. So, what is nuclear fission? What is the chemistry behind it? And how do these reactors even work? I'm Max Kirschling, and today we're going to talk about nuclear power. Uranium is the heaviest of the primordially occurring elements, with an atomic mass of 238.029 grams per mole. You can find it at the bottom of the periodic table in the actinide series, with the atomic number 92. It has 92 protons and 92 electrons, and is kind of like your crazy uncle at Thanksgiving, unstable. As a matter of fact, all the naturally occurring isotopes of uranium are unstable. While there are 6 known uranium isotopes, we only need to know about the 2 most common, U-238 and U-235. Nuclear fission is relatively straightforward. When a uranium-235 atom absorbs a neutron, it becomes an even more unstable atom of uranium-236. The nucleus of an unstable U-236 atom breaks apart spontaneously into 2 lighter elements, krypton and barium. In addition, 3 newly freed neutrons are released and heat is generated. Other atoms of uranium-235 can absorb those newly freed neutrons that have been released in the reaction, forming even more unstable U-236. Fascinating stuff right there. Did you know that nuclear power was invented over 2 billion years ago? That's right. Geologists discovered natural nuclear reactors in the Oklo region of Gabon in 1972. They found evidence that naturally formed pockets of uranium ore had undergone self-sustaining fission reaction, generating tremendous amounts of heat. That's all fine and dandy, but how do we harness this process in the modern age to generate safe and usable electricity? Well, the process is actually exceptionally simple, and it's a process that we've been using since the Industrial Revolution. A nuclear reactor consists of 3 primary elements: uranium fuel, a moderator, and control rods. The neutrons that are released from a uranium-235 atom undergoing fission are known as fast neutrons. These neutrons are moving too quickly to generate additional chain reactions. For this reason, moderators are used to slow the neutrons. Without the moderators, a sustainable chain reaction could not occur. With a moderator in place, we can slow the velocity of the free neutrons, ensuring additional fission reactions occur. Slowing the neutrons allows for a continuous chain of fission reactions, but what we really need is a controlled reaction. This is achieved with the control rods. Remember, each fission of U-235 generates 3 free neutrons. The goal is to create a continuous linear series of reactions. Left unchecked, an exponential amount of heat generation would lead to a meltdown. By controlling the number of spare electrons available at any given time, the number of fission reactions can be controlled. Control rods, usually made of boron or cadmium, absorb a certain amount of the free neutrons. It is impossible to always catch 2 of the 3 neutrons every time, so these rods are able to be lowered or raised if there is too much or too little heat being generated. I know what you're thinking. Back up, Max. That sounds very complicated, and you said that this was something simple. Something that we've been doing since the Industrial Revolution, if I remember correctly? Well, you do remember correctly, because believe it or not, all of this complicated nuclear chemistry is for one goal: heating water. With our uranium fuel, our trusty moderator, and our safety-inducing control rods, we are now heating water. These generators produce steam by turning water from a liquid into a gas, which is then used to turn a turbine, connected to a generator, and pumping electricity into the power grid.